Hi guys, my name is Vanness Choo, and in this video, me and my friend Goay Zhen are going to conduct a lesson on topic 6, which is application of Newton's law. So we will start with a new term called tension. When a flexible cord pulls an object, the cord is said to be under tension. So tension usually represented with T, and it has a unit of N, which is Newton. And in this image, they are pulling a rope. The tension is pointing towards the middle. Here's an example. A block of mass 3 kg is hanging from a spring balance attached to the ceiling of a lift. In this case, we have to draw the direction of tension first, which is always going to the middle of the string. And we will only take the part attached to the block. So going up is T, going down is the weight W. So find the reading on the spring balance when the lift is moving upward. So the reading on spring balance is actually T lah. And when it is moving upward, the T is greater than W. That's why T will minus W. Rearrange, we can get T equal to MA plus mg. When the lift is moving downward for the second one, F will be equal to W minus T because W is now greater than T. So rearrange, we can get T equal to mg minus ma. When the lift is moving upward but with a uniform velocity. So when it is a uniform velocity, F will equal to 0. When it is going upward, W minus T. Rearrange, we will get T equal to mg. So now we will get into static friction. It is a variable force that adjusts up to a maximum limit. The equation of static friction is this, where Fs is the static friction force and mu s is the coefficient of it. Fn is the normal force, and the inequalities means that the static friction force can vary from 0 up to the maximum value. And this is the maximum value where Fs max equal to the coefficient times the normal force. And the unit for static friction is Newton. Static friction, it acts on stationary object. It is an adjustable force that matches the push, but there is a maximum limit. This is why when we push something, there is a breakaway force needed before the object begins to move. Static friction is a smart force because it adjusts exactly opposite the applied force up to its maximum value. It is not a fixed number. So here we have an example. Let's say the maximum static friction is 20 Newton. So the first image, we can see that the force applied is 5 Newton. The static friction will match it, which is 5 Newton as well, to keep the object remain at stationary. In second image, when the force applied is 10 Newton, the Fs will also be 10 Newton. And now in the third image, when the force applied is 20 Newton, which is the maximum static friction, so the object will still remain at stationary. But when the force is increased, even just by 0.1, the object will begin to move because it has exceeded the maximum static friction. And so now we will look at one example question. The coefficient of static friction between hard rubber and a normal street pavement is about 0.90. This is the mu s. On how steep a hill at maximum angle can you lift the car apart? So to answer this kind of question, usually we will draw an image first. So this is the angle, and then there is a car parked on top of the hill. So when the car is parked, that means it is stationary. A stationary car means that all the force should be balanced. So this is the normal force, this is the frictional force, this is the y component of the weight. This is the weight, by the way. And then this is the x component of the weight. The angle is here as well. So we have to resolve the weight first into x component, which is w sine theta because it is not touching, and then y component is w cos theta because it is touching the angle. So Fn, because the force is balanced, Fn is equal to the y component, which is w cos theta, and then the Fr, which is the frictional force, is balanced with the x component of the weight, which is w sine theta. And now insert everything into the formula, that is FFR equal to mu s times normal force. So FFR is the w sine theta equal to mu s 0.90 times w cos theta. Now we will move w cos theta to the left side, which is w sine theta over w cos theta equal to 0.90. So w cancel out, and then this part can be simplified as tangent theta equal to 0.90. So theta is equal to tangent negative 1, 0.90. Theta is equal to 41.99 degree.
Hi, my name is Zhen, and now I'm going to present the side topic about kinetic friction. So, as we all know, static friction is what prevents things from moving, and so kinetic friction means that what happens when they start moving. We will learn three important things in this topic about kinetic friction, which is direction of the force, factors affecting its magnitude, and the formula. So the first thing is direction of the force. Kinetic friction is always opposes the motion of an object. So for example, if the object is moving towards the right, the kinetic friction is acting towards the left. If the object is moving upwards, the kinetic friction is acting downwards. Its main purpose is to slow the object down. So that's why it always opposes the motion. And the next thing is the factors affecting the magnitude of the kinetic friction. There are two main factors in this, which is the normal force and the nature of the surfaces. The normal force increases, which means if the object is heavier, the normal force will increase and the kinetic friction will also increase. The nature of the surfaces means that how rough or smooth the surfaces are, and it is measured using the coefficient of kinetic friction. And so that's why different types of surfaces have different magnitude of coefficient. And the last thing here we'll learn is the formula for kinetic friction. Since it is always a constant force, as long as the object is sliding along a surface, the kinetic friction force is always the same. And the formula, which is kinetic friction is equal to the coefficient of kinetic friction times multiplied by the normal force of an object. So now we'll move on to the question session. So for question 1, explain why it is easier to pull a thread at an upward angle compared to pushing it at the same angle. So the answer will be is because the normal force decreases, the friction will also decreases. This is because also the pulling upward gives a vertical upward component, so the normal force is reduced, thereby reducing friction, and so that's why it will become easy to pull. So for the question 2, I won't read the question, then straight away for the answer. So first, we will need to calculate the force that is acting right because we are pulling it, which is this force, and then we will calculate the force that is acting outwards because of our pull. And our total normal force will subtract the force that we pull and we will get this force, and the total frictional force is this force multiplied by 0.3, which is this force, and then our total force, which is our pulling force minus our frictional force, is this 0.21 Newton, and our F equal to ma, and so that's why our A equal to 1.121 meter per second square. Move on to the tutorial. So for this question, we can draw the diagram like this, and so we can deduce that the angle at here, this part is also 27 degrees. And since the net force is 0, the frictional force is equal to the force that is pulled down by gravity acting toward the side, sliding downwards. And so we cancel out, we get the coefficient of the kinetic friction is equal to tangent 27 degrees, which is 0.51. So for the last question, we have this, and first we need to find the normal force, and we will find the force that is acting downwards with the frictional force. We add up this together because one side is empty, they are in opposite direction. So our MB force acting downwards is this, and we will minus that to get our resultant force. And according to F equal to MA, our A will become to 1.55 meter per second square. And for B, our frictional force equal to this, so we will substitute a value inside. We will need this extra coefficient force, so that it won't accelerate. We plus the original coefficient, we will get this. Thank you.